So now what we'd like to do is find the expression for current as a function of time in an LR circuit. This is probably going to make you think of some of the things we did with a capacitor circuit, and in fact a lot of the things are going to work out to be close to the same. So we'll start with Ohm's law. As we come around the circuit, not Ohm's law, Kirchhoff's law, as we come around the circuit, the net potential has to be 0. So let's start by writing that down. So we'll write down Kirchhoff's potential law. Delta V of the resistor plus delta V of the inductor equals 0. And this is for the case we were just looking at in the previous video where we've switched it on and the current was already flowing, so we're looking at a current decay now. What is the potential difference across the resistor? Well, we get a potential drop across the resistor, so delta V is equal to minus I times R. There's our Ohm's law. And what is the potential across the ends of an inductor? Well, that's equal to minus L times dI by dt. And let's just make sure these signs make sense. For our circuit, the current is decreasing, which means that our slope, di dt here, is negative. This negative times this negative would be a positive. So the inductor would act as a potential source, like a battery, which is what we established that happens. So now what we're trying to find is what is the current as a function of time. So we're trying to solve this equation for I, where we know it'll have a t in it. So let's get our L di dt to one side. L di by dt. Bring that to this side, which means that's equal to minus current times resistance. What will we do with this? Let's get this I over to this side. L divided by I times di by dt equals minus R. This is looking better. Let's get our inductance L over to this side, and let's get our dt over to that side as well. So 1 over I di equals minus R over L times dt. One extra step we're going to take here, because I said this was going to end up a little bit like a capacitance circuit, I'm going to get my R down in the denominator. Minus 1 over L over R dt. So now I have an expression which I'm certainly able to solve. Like I said, we're trying to find I of t. So let's integrate both sides over appropriate limits. So on the left-hand side, we're doing an integral over current. So the integral of 1 over I di. What are the limits of our integral? Well, it starts with a current that we can call I0. This is our current at t equals 0. And we're going to integrate until it's some general value of I, which is a current at some value of time t. So the integral of 1 over I di equals the integral of minus 1 over L over R dt. Our time is going to integrate from t equals 0 to some general time t. So where is this going to take us? The integral of 1 over I is the natural log of I. That's going to be evaluated at I and I0. When I do my integral over here, first thing I do is I take my minus 1 over L over R outside. The integral of dt is just t. That's evaluated at t and 0. So when I put in my limits, I've got the natural log of I minus the natural log of I0 equals minus 1 over L over R times t minus 0, so just t. Okay, this kind of looks nicer now. Natural log of I minus natural log of I0, I can divide those arguments. I think this slide's getting a little bit full, so I'm going to move on to a fresh sheet of paper. So if I divide those arguments now, that gives me the expression natural log of I divided by I0 equals minus 1 over L over R t. I said we were trying to get an expression for the current I, so we'd like to isolate I. The way to do that is let's raise both sides to the e. So e to the exponent of natural log I over I0 gives us I over I0 equals e to the minus 1 over L over R times t. Here we'll introduce a new definition. Let's introduce L over R as tau, our time constants. So we'll define tau equals L over R. Hello, Pippin. You are a very good boy. Sorry, the dog just came in. I'm kind of used to speaking. We define tau as L over R is the time constant for this circuit. Similar sort of thing that we had for a capacitor circuit. So now I'm going to bring my I0 up to the other side. Minus T over tau. So there's my expression for current as a function of time in an LR circuit that starts off charged out. So I0 is the initial current. So what does this tell us about the shape of the current? So this tells us that the current is going to die off exponentially. We could make a graph of this current if we wanted to as a function of time. We did that when we did our charge and our capacitors. Just if you want to know exactly how close he is to me, he is about 3 inches from where I'm filming this. Hello, Pippin. Okay, so there's my company. If you hear wags and barks and licks, it's because I don't want to start over. So I could do a graph of current as a function of time. My current would start with some finite value of I0. So it starts here at I0 and it falls off exponentially. So it kind of falls off like this. Just like our RC circuits, this current will never truly get to 0, but after about 5 time constants, it gets pretty close. So if you were talking about it being completely discharged or the current gone to 0, we mean after 5 time constants. Okay, there's our equations worked out. The next thing we'll do now is do a few examples about working these things out.